Hello, this is a video on how to show you the work on how to calculate Gay-Lussac's, which I used to call no name because I didn't know that was the name, no name law. So maybe sometimes you'll see the word no name law, and that's Gay-Lussac's law. So if this is the first time you watched a gas video example of showing work, then I'm going to talk a little bit about the steps you need to follow to do the work, because there's really one way of doing gas calculations. If you have already seen a previous gas law explanation video, then you can skip through this. So there was another video on the overall gas calculations where I kind of describe how you do all the different types of gas problems. When you do gas problems, there are several questions you ask yourself to figure out which equation you're going to use or which concept you're going to use. The first question you ask yourself is what I call conditions. How many conditions do you have in the problem? What that really means is look at the gas question and say, are you doing something to the gas? Are you compressing it? Are you cooling it? Are you heating it? And if you do see those action verbs, then what's happening is you're actually starting with the gas with one condition, which I call condition 1, which has all the 4 variables: pressure, temperature, number of moles, and volume. And then you're doing something to it, and therefore now it has a final or new volume, pressure, temperature, and number of moles, which I can call condition 2. And that's what the little 1 and 2 subscript means when you see the mathematical relationships. So if you do see these action verbs, you have what I call a 2-condition question. If you don't, and the question is just like describing the gas, then you have what I call a 1-condition question. It's important because with 2-condition questions, there's actually, so that's the first question you ask yourself. And once you figure that out, you go to the second question. If you have a 2-condition question, what you need to know is you need to know what's being held constant and what's varying. Now, for the 3 gas laws and Avogadro's hypothesis, which this is one, you have 2 things being held constant and 2 things that are changing. Okay, once you know that, then you can set up your mathematical relationship with the variable you're looking for, x, on one side and all the other variables on the other side. Now, if you look, I kind of skipped to step 4, and I didn't do step 3. Okay, you can do step 3 or 4 in either order, but if you do get the mathematical relationship first, you still have to declare all your variables for that math equation before you plug in. Okay, and of course you declare all the variables and get them into all the units that are appropriate so that they will cancel out as much as possible once you plug it into the equation. And once you plug it into the equation, you do your math, and then you get your answer in the correct unit or the closest correct unit. And if you need to do a little bit more converting, you convert, and then you get your answer and your final answer with the correct number of significant figures and units. So that's the basic steps to follow for any gas problem. So we're looking specifically at Guy-Lussac's law problems. It is a part of the gas laws, which means it is a 2-condition problem. And you can see in the question it says if I increase, and increase is an action verb. So you know you're going to start out with the gas at 1 condition. That's where the subscript 1s are. And then you do something, and then you new condition, which is a subscript 2. For Gay-Lussac's law, you may have done the gas demonstrations already, or you may have done some other read in the book or something. And what you figured out is that for Gay-Lussac's, what is being held constant is the number of moles and the volume of volume, and pressure and temperature is changing or varying. So using our little analogy of people, students in a room acting as gas particles, what we have here is that we're going to keep the room volume the same, and we're going to keep the number of students inside the room the same. And what we're going to do, you can do it either pressure or temperature, but temperature is easy to understand. If I increase the temperature, meaning if I tell the kids to walk faster, will there be more hits on the wall or be less hits on the wall for a given time? Well, of course, if you keep the same number of people and the volume of the room is the same, and you increase how fast they walk, of course they're going to hit the wall more often. So therefore, as the temperature increases, so does the pressure, which, as you know, is a direct relationship. And as you know from previous chemical concepts in the class, if you're setting up an equation where x variable, the variable you're looking for, is on one side of the equation, equal sign, and all the other variables on the other side, if you have a directly proportional relationship, then your variables are one's on the top and one's on the bottom. Okay, so when you have your P1 and T1, the T1, if it's T1's on the top, then P1's on the bottom. Or if P1's on the top, T1's on the bottom. And if you look, since the question is looking for the new pressure, P2, well, P2 is equal to P1 times the ratio of the two temperatures. So the real question is, where's T1? Well, if they're directly proportional, if P1's on the top, T1 must be on the bottom. So therefore, the only place for T2 is right there. And this is the equation I want you to set up. Okay? And yes, I understand that you could set up the ratio at condition 1 equal to the ratio at condition 2. But this is actually a lot better because what it shows you is that P2 is actually some function of P1. And that function is a relationship between your two temperatures, how your temperature is changing, which should make sense. Okay, so now you have your variable. Now you come over here and you declare your variables. So if you look at the question again, usually in word problems, one sentence is one condition. So it tells you have a pressure of 1.35 atmosphere, condition 1, so it's P1. Temperature is 125 degrees C, T1. Now remember, the biggest thing is with temperature is you got to be in K to do the calculations. It's so important that if you do a calculation in degrees C with temperature, you get absolutely no partial credit. It's all wrong. Okay, so make sure temperatures are always in K. So it says then I increase the temperature to 250. And of course you put in the K, and the P2 is what we're looking for. So you plug in, K's cancel, and you get a P2 of 1.773 atmospheres, which you change to 1.77 atmospheres. Okay, and if you want, if this says, you know, what's the new pressure in a different unit than that, then you could have. What you could have done is you could change the units here, or kept the units in atmosphere, and then change it here into another unit. Okay, so that's how you do Gay-Lussac's law. Now I picked these numbers because if you look, 125 degrees C to 250 degrees C is actually twice. So if you didn't change your units into K, you would have thought that temperature, the new pressure is twice the temperature, twice the pressure atmospheres, of the original condition, which would be 270. And as you can see, that is not correct. And that's a, I mean, that's just a mathematical way of saying you got to put the degree C into K. But it's important that that you put your degree C into K, because the math isn't going to work unless you do. Okay, and we'll talk about that in Charles's law. Okay, so that's how you calculate Gay-Lussac's law.